Okay, so this next section we're actually going to be going through pretty quick. This is in chapter 1. In the text it says, what is it? From the Big Bang to the blue marble, right? Okay, and that's the chapter 1. The many lectures before was the prelude material. Okay, so this section, because of how much goes into it, we're going to go through quickly and just get the main ideas here. So you've probably all heard about the Big Bang before, and we're not going to go into the details of how the Big Bang theory works or anything like that. Just realize that at some point, all materials actually came from one central point and then expanded slowly out from there. Okay, I wouldn't say slowly; I would say very quickly out from there. And slowly over time, that material actually coalesced together to form nebulas, and then those nebulas form together to form planets, sometimes planismals, and then suns and things like that over time to form our solar system and ultimately our Earth. Okay, now we think that first initial expansion of that bit, or what we call the Big Bang, or the initiation of our universe, happened about 13.7 billion years ago. Now, there's not very many dates I ask you to know, except this is one of those. There's two basic dates that I ask you to remember. One is 13.7 billion years, and that's when the universe is thought to have started to expand. And then one is about 4.5 billion years ago, and that's when we think our Earth was formed, or our solar system was formed. Okay, we'll talk more about that as we go through this. Okay, so this all began right after that Big Bang, when the universe began to cool. At the time, most of the matter was just a form of subatomic particles. So these were like things like what we call quarks, and which are what protons and neutrons are actually made up of. And electrons are what we call a subatomic particle as well. But slowly over time, they actually start to coalesce together. As they start to cool off, they can start to coalesce together into what we call nuclear fusion. Initially, that nuclear fusion was not able to happen because there was too much energy. But as it started to the temperatures decreased, the particles then could collide together or fuse together. And when they do that, it lets out a lot of energy at the same time. So you can get a proton and a neutron coming together to form what we call deuterium, which is an isotope of hydrogen, right? Now, as these collisions continue to occur, you start to form bigger atoms. Okay, so you'd get a deuterium and a helium together. Okay, and you can get helium-4. Okay, or you get a deuterium and helium-3 together. You can also get a helium-4. It depends on which ones they have. So now remember, hydrogen is the most basic atom, which means it has one proton in it. Whereas helium is the next most basic atom, which has 2 protons in it, right? And then it goes down the list from there. So you have helium, and then beryllium, and so forth down the list. And the definition of an atom really is the number of protons it has. That's a very important point that a lot of students have a hard time remembering. But the definition of an atom is the number of protons it has in it. So if it has 1 proton, it's hydrogen. If it's 2 protons, it's helium, and so forth down the line. Okay, and so during this time frame, in what we call the Big Bang, this is what we call nucleosynthesis, when the actual atoms were synthesizing together or forming together. Okay, and nucleosynthesis, or the whole basically creation or formation of the periodic table, or the atoms that form up the periodic table, come in one of 3 ways. The first one is what we call the Big Bang nucleosynthesis, and this was so hot, the material was so hot that you really could only form hydrogen, helium, and small amounts of beryllium and lithium. Okay, but as that material slowly continued to cool off, now it could that material would start to coalesce into large balls, okay, or stars in a sense. So, for example, our star, the scientific name for our star is Sol. And it is 95% of all the mass in our solar system is in that star, okay? But hydrogen actually forms out the vast majority of that star, or that sun. Okay, so inside of a star, those atoms can still start colliding together, okay, or forming together. And this is what we call stellar nucleosynthesis, right? So, for example, you can get a hydrogen and a hydrogen together, and that would become the heavier hydrogen, which would be deuterium. Or you can get helium and helium together, helium-3 and helium-3, and you can get a helium formation and also 2 hydrogen. But there's lots of different ones. You can first start forming hydrogen, burning hydrogen to form helium. And then you burn helium to form carbon. And then carbon to form oxygens all the way down the line until you get to iron. Iron is the end of the road. Iron is the furthest you can go in a star to burn that fuel. Okay? And there's some great videos on this, and I'm going to post those videos for you guys to watch. But they're great videos to watch for it. Okay. Now within that star, it will continue to actually burn. Start off with hydrogen, then we'll go to helium, carbon, oxygen, neon, magnesium, silicon, and all the way down to iron. Now all the stuff before iron is what we call exothermic reactions, which means when they combine, they actually give off energy. Okay, they give off energy, and they don't use as much energy as they give off. Okay, whereas an endothermic reaction, now it's actually taking in more energy than it gives off when it actually ruptures. So at this point, when you start burning iron, it's taking all that energy from the star instead of giving more energy to the star. Okay, and so as it takes that energy, it takes more and more energy over time until what's happening is that material on the outside of the star is actually expanding faster than the material on the inside, and it basically collapses in on itself. We call that a supernova. And when you have a supernova, all of a sudden all that material that was forming together before, we call stellar nucleosynthesis, can now form into what we call a nuclear. When we do a supernova, all the other materials can form. So before, in the Big Bang nucleosynthesis, you can only form really hydrogen and helium and scant amounts of beryllium and lithium. And then when in stars, you can start forming hydrogen all the way up to iron, and sometimes other things as well with different parts of it. But then all the rest of the atoms come from the actual explosion of these stars, or what we call supernovas. Okay, so Okay, sorry for the pauses there. My kids keep trying to come in and interrupt. Okay, so this is a great quote that I love. It says, "The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, and the carbon in our apple pies were all made in the interiors of stars. Gold and jewels, tungsten and light bulbs, and silver and cookware were all produced during stellar explosions. We ourselves are made of star stuff." Okay, it's kind of cool. All the atoms inside of us were at one point inside of a star. Okay, and so all the atoms that we have, all the material that we see around us, was once a time formed within either the Big Bang, okay, within a star, or when a star explodes when it goes supernova. Okay, one of those are the only ways that really these atoms are forming. Okay, and that's so all of them have, at some point come from these aspects. Okay, so I wanted to watch a video here. Let's see if I can get it to work. Hopefully it works here.